In this webcast, we will continue our discussion of recognizing resonance contributors by comparing a linear and a cross-conjugated system. Now, a linear conjugated system is very similar to a type of system you've seen before. In this case, we have this lone pair on the nitrogen donating in, did an N to pi star interaction, donating into the series of pi bonds and localizing up onto the oxygen of our carbonyl. Every arrow that we draw is valid, and we've created a valid Lewis structure for our structure on the right. So this is a linear conjugated system, linear because we can donate those electrons from our nitrogen into our carbonyl oxygen. Now a cross-conjugated system, example of that is shown here. Now just by a change in position of our nitrogen from one carbon to the next, we create this cross-conjugated system. Now this cross-conjugation is defined as a contiguous arrangement of atoms whose hybridization includes p orbitals, but there's no means for electron flow, which we can also call broken connectivity. This connectivity leading from our lone pair, our electron source, to our oxygen, our electron sink, has been broken. So to show that to you, I can start on my lone pair and I can start drawing some electrons here. Now the first thing I would do is draw an arrow to that carbon-nitrogen single bond, create my double bond. Now I have 10 electrons around that carbon right there in the middle, so I have to move 2 of them. Now the only pi electrons that I can actually move are those between that carbon and the carbon of this carbon-carbon double bond. We can't, there are no pi electrons that we can push up towards the oxygen of our carbonyl. The only ones that we can move are part of that alkene. So we're stuck pushing them onto that bottom carbon. There's nowhere else for them to go. And once they park on that carbon, our flow has been stopped. So this is an example of our cross-conjugated system. Drawing the arrows there. This nitrogen and carbonyl, they're cross-conjugated. We cannot push them from the nitrogen all the way up to the oxygen. On first glance, looks as though there's a contiguous pi system between the two, but until you actually push the arrows, you will not know whether they're linear or cross-conjugated. So therefore, that lone pair will not donate into the electron sink of our carbonyl. Now another example I'll work through for you here. This example is the amine lone pair delocalized all the way into our nitro group. Well, at first glance, looks like it, sure, but the only way to find out is to actually draw our arrows and go through the steps. So we start with our lone pair on our nitrogen. Start moving along, going through this benzene ring, just as we normally would. Now we stop at this point to do a check. We see that we have 10 electrons now around that carbon in this resonance structure. We have to move 2 of them away so that way our octet rule stays intact. The only pi electrons that we can move are part of this carbon-oxygen double bond, part of the carbonyl. There are no pi electrons that we can move to donate into our nitro group or part of that benzene ring. So we're stuck, once again, by parking them onto our oxygen. So is the amine lone pair delocalized into the nitro group? The answer is no, it is not. It is delocalized into our carbonyl, but not all the way to the nitro group.